Hi everybody. Today we're going to look at section 2.1. So section 2.1 and 2.2 are both on the first exam because the subject matter deals more closely with stuff we saw in chapter 1. In fact, you're going to recognize some of these concepts as things you've already done. The main difference here is that we are just defining everything very rigorously. So in a very precise manner, so we can use these precise concepts later on. So the general setup here is that we want to compute the slope of the secant line, and we've already defined that in section 1.4 as the MPQ function, right? It's a function of x. When p is a fixed point, and we want to know what happens if we bring q, which is a moving point, what happens if we bring q closer and closer to p? What happens to the slope of the secant line? And as we saw earlier, as q gets closer to p, the slope of the secant line gets closer to the slope of the tangent line. And we did problems in section 1.4 where we were able to estimate the slope of the tangent line. But we really weren't able to prove that any of those were in fact the slopes of the tangent lines. I did a problem similar to this later on in chapter 1, where I redid the problem about the object falling from the CN Tower in Toronto. And I was able to prove that the instantaneous velocity of that object was 49 meters per second. But instantaneous velocity is a physics problem. We want to do this more generally for every kind of function, for slopes and tangent lines, not just physics problems. So that's what we're going to do. We're going to look at the general form of this. So what we're going to do is we're going to define the tangent line as the curve that is tangent to the line. So the line is called the tangent line. So they're tangent at the point P. And the slope is just the limit of the MPQ, right? This formula here, that is our secant line. So we just want to know what's the limit of these secant lines as Q gets closer to P. And we're going to call that the slope of the tangent line. And that tangent line, we will have a point and a slope, so we can use point-slope form to find the equation of the line. So the strategy here, when we solve problems like this, is I'm not going to worry about the limit right away. The reason I do it that way is just it makes your workspace a lot less cluttered. Do all the algebra first. Plug all the numbers in, simplify, then you can go ahead and tack that limit on at the end, evaluate the limit, and get m. So I'm kind of working right to left here. And you'll see how that works in this first problem. So here I have a parabola, and I want to know what is the equation of the tangent line at the point negative 3, 3. So here's negative 3, 3. It's like right about here. We can see that it's going to have a negative slope and a negative y-intercept. So as a hint, you guys may want to graph your homework problems. You're not required to, but you may want to anyway, just so that you can see, is this slope going to be negative? Is it going to be positive? Is the y-intercept going to be negative? Is it going to be positive? So if you make an arithmetic mistake, maybe you compute it and get a positive slope. If you know the slope has to be negative, then you know that you computed it wrong. So it's a good way to get a general idea about what the answer should look like. All right, so here's everything we know. We know f of x, we know a, we know f of a. You must be given f of x, you must be given a. In this problem, we were given f of a, but in some problems you may have to compute it. Now what I'm going to do, I'm going to plug all of these known values into this part of the equation here. I'm not worried about the limits right now. You don't need to worry about the limits in the beginning. It's easier to do the algebra without all these limits hanging around. So notice I'm just plugging in everything I know. Just plopping it right in there. Then I'm going to simplify. So now I have a rational function here. if you try to evaluate the limit here, you could put the limit back on, right? Because that's what we want. We want m. M is the limit of this as x approaches -3. But you can see we're going to have division by 0. And what we saw in section 1.6 is that anytime there's a division by 0 situation, we're able to factor this thing to get rid of that division by 0. So that's the next goal. Right? We want to factor the numerator and then cancel that x plus 3 out of there. Now that we've done that, when we're ready to evaluate the limit, we can just plug -3 into that value, and we're done. That tells us the slope. And that's actually what we do in the next step. So here, we have to compute m. M is the limit of this, right? That's the definition. Which, just plug everything in, that's this. Can't plug in -3, so I'm going to replace this expression here with this, right? So it's just the limit as x approaches -3 of x minus 1, which now we can use direct substitution, plug in -3, and get -4. So that's the basic idea. We're going to use this strategy for basically every problem in this section, and for the homework problems as well. So one thing I want to point out, if you guys are using the homework tutor, or if you're looking at the solutions, so after the homework closes, you can log back in and look at worked out solutions. The solutions often have all of the algebra combined and sort of done at the same time. Unless you have very rock solid algebra skills, there's going to be a tendency to make mistakes just from the notation, because there's going to be big fractions and all kinds of stuff. The way I like to do it is break everything into very small bits, solve the little bits, and then reassemble the pieces. So the way I do it requires a little more organization, but if your algebra skills aren't perfect, that's okay. You can work on your organization skills as well, which will definitely come in handy in this class and any future class. So this is m, -4. Now, I know 1 point on the curve. I know -3, 3 is on the tangent line. And I know the slope is -4, so I'm just going to use point slope form and solve it. So from here, everything's really easy. If you guys want to double check all the algebra and the arithmetic, go ahead and pause the video and do it now. I'm going to move on and show you just a visualization of why this works. So this visualization that I'm going to show you, this is in the ebook. And I picked a problem that looks really similar to the problem we just did. It's not quite the exact same problem, but it's pretty close. So what do we have here? So for the problem here in the ebook, the point is -1, 1. And the graph is just y equals x squared. And the slope is -2. So you could solve this problem just as easily. But this is about why the tangent line idea works. So we really haven't talked about this that much. It's in the book, but I haven't addressed it yet. So what does it mean for something to be tangent, right? And why are we allowed to use this technique? So the reason this works is that as I zoom in, so I'm going to move this slider to the right, and it's going to zoom in on this point. So right now, it's really clear. The curve is in black, the tangent line is in red. So what do you think is going to happen when I zoom in? Well, if we're using the tangent line to approximate the slope of the function at that point, that means that the closer we get to the point, the flatter that the function should get. And eventually, we should not be able to tell the difference between the original function and the tangent line. So let's start zooming in here. Doesn't take long before they look basically the same. So here's 50 times magnification. And that should make sense, right? Because as we zoom in, the slope of the secant line gets closer and closer to the tangent line, which means the secant line, because it's getting closer, the whole curve is coming with it, right? The secant line has 2 points that lie on the curve. And we can slide this around anywhere we want, right? So what if we go here to the bottom, right? What if we go right to the vertex? You can use the arrow keys on the sliders to get them really precise. So what happens if we zoom in here? Yep, see how it flattens out? Curve, flat, because we're zooming in. And that works with all functions of a certain type, right? So here's a funny looking function, right? So we can pick any point on here and just zoom in, flattens right out. And that's the idea. So this is actually going to lead us to something much later in your math careers. At the end of Calc 2, you're actually going to prove that as you get closer and closer, the distance between these curves goes to 0. You're actually going to prove that. Okay, so that's the tangent zoom. So I just want to show you that. That's some justification for some of the stuff that we're doing here. Right? So when we see this here and you say, well, how do I know that that is indeed the tangent line? Well, the idea is if you zoom in, it gets closer and closer. And you can see it's very, very close. But this is true for any function where the tangent line at a certain point exists. And it turns out that's not everywhere. We're going to see where you can have tangent lines and where you can't. We're going to see that very soon. All right, so what we're going to look at now is a slightly different formula for the slope. And so you might be thinking, why do we need two different formulas? What was wrong with the one we had? Well, nothing's wrong with the one we had. But there might be situations where this formula is more useful for one reason or another. So what we're doing is we're just going to relabel that picture. This is the same picture. So we still have P. It's still A f of A. But notice there is no more x. We have taken x out of the equation, literally in this sense. And we've replaced this idea of x minus a is now h. So we're calling h this very small horizontal distance at the bottom, right? You can see it here with the triangle. So this was a, and remember this was x. So x minus a, we're just calling h, which means x is a plus h. So where we had f of x before, we're just replacing it with a plus h. F of a stays f of a as our previous formula. And what used to be x minus a is now h. So it turns out that this is exactly the same formula. The reason that this works better in some cases is that now, instead of doing x approaches a, we're just going to have h approaches 0, which means no matter what our function is, this limit always is the same. We don't have to figure out, are we getting closer to 2 or getting closer to 1, right? It doesn't matter where p is, right? Because that does not appear in the limit. Now, p, the value of a here in p appears over here, but that's okay. So let's see how to use this. Sometimes I prefer this formula, sometimes I like the other one. We'll see how it goes. So let's jump in and do another problem just like the one we just did. We're going to find the equation of the tangent line. We have a curve, and it's at the point x equals 4. So what's my strategy here? So I know f of x, that's the curve. Notice it says x equals 4. There is no a anymore, right? We're going to call that a, right? So when it says at a point, don't worry about how it's labeled. Remember, when we say a, we're talking about the coordinate x equals a. So when it says x equals 4, that's really saying a equals 4. So what's different about using this formula? Well, I don't have to worry about h. H is just going to be h. I don't have to worry about f of a. I can compute that. But I'm going to have to compute this f of a plus h ahead of time. And you'll see why as we get into the problem. You don't want to do a bunch of algebra inside these big limits. pull the pieces out, compute them, simplify them, put them back in, compute a larger piece, simplify it, put it back in, and then compute the largest piece. So kind of work from the inside out on this, or looking at the formula from right to left. All right, so the first thing here, just write down everything we know, right? So we know the function. We know a is 4. We know f of a is f of 4, so we just plug 4 into the function, right? So that's 3. So we know f of x, a, f of a. But we should compute f of a plus h as a separate step. Sometimes the algebra on these things gets really wacky. This one's fairly straightforward, as you can see. But look at what I'm doing here. F of a plus h. A is 4, so I'm just plugging 4 plus h in here for x, which is 2 times 4 plus h plus 1. So I'm just replacing this x with, it's a plus h, but again, we know a is 4. So anytime you plug it into a formula, we can just plug in 4. So you simplify this. 2 times 4 is 9, and 2h. Right? Sorry, 2 times 4 plus 1 is 9, and then 2h. So we plug all these things into the next biggest thing, f of a plus h minus f of a over h. And you can see why you kind of don't want to do a bunch of arithmetic inside these big limits. You're allowed to do it that way. I'm just cautioning you against it. So here's f of a plus h. Here's f of a, right? And h stays h. Now, we would like to evaluate the limit of this as h goes to 0. But clearly we'd be dividing by 0. In fact, it would be 0 divided by 0, which means a hole in the graph. Anytime you're computing these tangent line problems, it will always be 0 divided by 0. So what do? Now we start to use the techniques we developed in section 1.6. We need to get this h out of the numerator and cancel this h in the denominator. So the way to do that is to use the conjugate. So this is the very similar problem to what I did in section 1.6. You just flip the sign and you multiply this expression by 1. So here we have a number divided by itself, that's 1. And so this is the conjugate. So what we're going to do is we're going to FOIL this thing across, and we're not going to FOIL the denominator across. So we're going to FOIL the numerator, we're going to not FOIL the denominator. Right, so this is another difference of squares. Looks very similar to that problem we did before. And you had some on the homework that look like this. So radical 2h plus 9 squared is just 2h plus 9 minus 3 squared is 9. Now we simplify the numerator, and you can see what's going to happen. We're going to end up with just these 9s are going to cancel, and then we're going to cancel the h's. So we're just going to be left with 2 over radical 2h plus 9 plus 3. So what we've done here is we've turned this expression, which was this, into this. Now we can evaluate the limit. Okay, so the limit here said, the limit of this, we're just going to replace this expression, the way it was originally computed, with the equivalent expression. And now we can plug in h equals 0. So we can use direct substitution now. And we get 1/3, which works out really nice. Now we compute the tangent line. We have a point on the graph, right? If you go back to the previous page, right? We have the point 4, 3 is on the graph. And now we know the slope is 1/3, so you plug everything in. And you end up with this nice formula, y equals 1/3 x plus 5/3. So this is pretty much what we do, at least for the first couple sections of chapter 2. So most of the rest of this section looks like this, and the next section looks like this. So let's go back and look more at instantaneous velocity. We already know how it works. We saw a different formula of instantaneous velocity earlier, right? Section 1.4. Well, here's the updated version of the instantaneous velocity. It's just the limit of the average velocity, right? So this thing here is the average velocity. The average velocity is the equivalent to the slope of the secant line, but we don't need graphs here to do velocity. So all we're doing is just renaming this expression that we saw in the previous problem. We're just calling it velocity at the point A. These problems work exactly the same way, and we even use the same strategy. So if a ball is thrown in the air with a velocity of 40 feet per second, its height in feet after t seconds is given by this equation. Find the velocity when t equals 2. So here a equals 2, so we have to compute f of a. We have to compute f of a plus h, and then we're going to plug everything into the formula. So I went ahead and just did all the work for you. So here's f of t. A is 2. F of a is 16, right? Just plug it into the equation. Now we have to compute f of a plus h separately. Again, you don't have to do that. I highly recommend you do it. This is a lot of arithmetic here, guys. A lot of algebra. I don't think you want to do this much algebra sitting inside a bigger problem. So we plug in at a is 2, so f of a plus h is 40 times 2 plus h minus 16 times 2 plus h squared. I'm going to let you do the algebra on that. You have to FOIL the square. I'm not showing those algebra steps. You don't have to either on a test. Because a lot of people can do this kind of stuff in their head, which is fine. But you do need to show the individual steps, right? You can't just, start here and end up here, right? You have to at least show what you're plugging in. So f of a plus h minus f of a over h is this whole expression. So I just took everything I computed before and plugged it in here. Now I'm going to simplify before I take the limit. Right? Those 16s cancel. And I drop the parentheses. Now I need that h to come out of the denominator. So I'm going to factor out an h in the numerator. Then I'm going to cancel it, and I'm left with negative 16h minus 24. So the limit of this expression, or this one alternatively, so the limit of the most simplified form that has an h in the denominator is the same as this. So when I want to compute the limit of this whole thing, well, this whole thing is equivalent to this. So I'm just going to plug this in instead. Now I'm not dividing by 0, so I'm allowed to plug in 0. And I get negative 24. Don't forget, when you're doing word problems, when they have a physical manifestation or physical meaning, make sure that you write out your answer in words, right? And use units, right? Okay, so now we're going to move on and define what is called the derivative. So the derivative is the most important word for the next 2 chapters. And you're going to do a derivative in this class every single day except maybe the first day you do chapter 4. I think there's no derivatives. And so the derivative is just the same stuff we've been talking about. It has a new notation, so when I write up here definition, that means you have to know what this means. So the derivative is either the slope of the tangent line, it's the instantaneous velocity, it's the rate of change of the function, the instantaneous rate of change. Any of those things are equivalent, and we denote it with a prime, like a little apostrophe. And so if we take the derivative of a function at some value a, so some point on the function, the derivative of a is just the slope of the tangent line or the instantaneous velocity. Either formula is fine. So these are equivalent. If the limit doesn't exist, then we just say the derivative does not exist. All right? so let's see how to use this. So let's find the derivative of f at x equals a. So when it says find the derivative, it means the slope of the tangent line, right? And that's what it says at the bottom. So I went ahead and just kind of reminded you guys that you can use either one of the formulas we've seen before. It doesn't matter which one you use, just whichever one works best for you. There are some things that are easier sometimes. So given the choice, if your problem has fractions or polynomials, I would use this one because it's easier to factor than it is to FOIL. That's all. So, because you have to FOIL this and you don't have to FOIL this. All right, so let's jump in and do this problem. So we want to know the derivative. So it's the same calculation as the slope of the tangent line. So let's go ahead and do that. Write down everything you know, right? F of x, a, f of a. Now, because I'm going to be computing one of these two formulas, if you're using this formula, compute a plus h ahead of time. If you're using this formula, you don't need to do anything ahead of time. You can see that I probably don't want to plug in a plus h in here, because then I have to FOIL it and all kinds of ugly stuff's going to happen. So I'm going to use this formula. So you plug everything in to what you know, right? So I'm using the first formula here. And you can see already that we've inserted a fraction inside another fraction. So you need to know your algebra. You need to know how to solve this. In fact, the entire rest of this problem is algebra. There's no more calculus in this problem, right? I mean, well, there'll be a limit. Sorry, there will be a limit at the end. So there's one step of calculus in this whole problem and 9 steps of algebra. So we need to get a common denominator, right? Because you have to subtract that 10. The only way to do it is get the common denominator. So x minus 2 is the denominator. So we're going to multiply 10 by x minus 2 over x minus 2. Notice that the fraction is still stacked over x minus 3. It's pretty ugly. You could pull that to the front if you want, but it should be fine. So I went ahead and distributed the negative 10 here, right? So minus 10x minus 10 times minus 2 is plus 20. And then you just bring everything together. Now I'm going to simplify that numerator, and I'm going to combine the denominators together, right? So I'll go back one more time, right? So it's x squared minus 10x. We have plus 1 and plus 20, so that's plus 21. And then I combine the two denominators. Now, we still can't plug in x equals 3, right? Because we'd love to, right? We want to just plug in the limit. But we know that that's division by 0, and we also know that x minus 3 will cancel if we factor the numerator. So go ahead and factor the numerator. Go ahead and cancel the x minus 3. That'll leave you with x minus 7 over x minus 2. And now we're ready to attach the limit back on. So m, the limit of the slope of the secant lines, is the slope of the tangent line, which is the same as this expression, this simplified expression. Now that we're allowed to plug in 3, we plug 3 in here, you get negative 4. So, not too bad. So let me back up just to remind you what happened again, right? We wanted the derivative. Remember, the derivative is only the slope of the tangent line. If it says find the tangent line, you have to keep going, and after you find the slope, you have to find the line. You have to use point slope form. When it says derivative, the derivative is only the slope. So we're able to stop when we get here. This is the end of the problem. So the derivative is the same as the instantaneous velocity if it's that sort of problem, or the same as the slope of the tangent line if it's that kind of problem. So here's a general strategy for solving problems. I used these strategies already in the examples I showed you. So first thing is choose which derivative or instantaneous velocity formula to use. You can use either one. Identify the value a and compute f of a. Just go ahead and get that out of the way, because you might forget to do it, and then you're going to be left with this f of a in your equation, and you go, well, what happened? Where's my f of a? Go ahead and compute it right at the beginning. F of a appears in both formulas, so just get it out of the way. If you use the second formula, you have to compute f of a plus h, which always involves a common denominator, foiling or multiplying by the conjugate. Plug all known and computed values into the derivative or instantaneous velocity formula. So that's what I did in the examples I showed you. Simplify and cancel terms so direct substitution can be used. So when we say cancel terms, in this formula, the x minus a has to go away. It has to, a factor of this has to appear in the numerator. And on this one, same thing. You have to be able to factor out an h by itself. If you can't do either one of those things, you made a mistake, you have to start the problem over. Or at least start the algebra over. And last step, if necessary, use point-slope form to find the equation of the tangent line. So sometimes you're just asked to find the slope of the tangent line. You're finished after step 5. If you're asked to find the entire equation, you have to keep going. All right, we got one more thing to talk about in this section, and it's what do we use derivatives for? So in my introductory slides, I showed you guys just some examples of what we can use this stuff for. So I'm going to go ahead and just pull an example essentially at random about how to apply derivatives. So we've already seen the math and physics, and those are not the only ones, right? In math, derivatives can be lots of things. In physics, they can be lots of things. But this is just what we've seen so far. Later in Chapter 2, we're going to see marginal cost. And on the homework, you have problems about application problems that involve chemistry or biology. And there's an entire field of mathematics called differential equations that involves solving problems with unknown derivatives. Some of you are going to take a class called differential equations. It's basically, it'll say the derivative is blankety blank, find the original function. And there's an entire class just of that. Actually, there's many classes, but there's one class that most of you have to take. All right, so we're going to look at the example of population growth. So we're going to look at bacteria in a petri dish. So the number of bacteria after t hours in a controlled lab experiment is n equals f of t. So the number is somehow some function of time. What is the physical meaning of the derivative, f prime of t? What are its units? So this is an example of a critical thinking problem where you're not looking the answer up. You have to know the meaning, right? So let's think about it. The slope of the tangent line, the instantaneous velocity, what are those both? Well, it might be easiest to use the instantaneous velocity as an example. If we know the position of a falling object, then the derivative is its velocity. So the derivative is how far it moves, so its change in position, divided by its change in time. So if its position is measured in meters, then the derivative is meters per second. Well, seconds, that's time, that was our variable. So here, if the number of bacteria is our quantity, then the physical meaning of the derivative has to be quantity per unit time, because our independent variable is time. So if it's bacteria, then the units for the derivative would be bacteria per hour, right? Or how many bacteria are added every hour. Maybe the change in bacteria per hour, something like that. And so this works. This is one idea that works for lots of applications. If you have a physical quantity, its rate of change is just the change in the dependent variable divided by the change in the independent variable. as units. We're going to get a lot deeper into this stuff later. This is just a first look at it. All right, B. Suppose there's an unlimited amount of space and nutrients for the bacteria. Which do you think is larger, f prime of 5 or f prime of 10? So again, you have to think about the physical meaning of this. If there's nothing stopping the bacteria from growing, and f prime is the number of new bacteria added every hour, think about it. Initially, if you have just a few bacteria to start, there might be 20 new bacteria added per hour. But then later on, when you have many more bacteria, there might be 80 added per hour. So because each individual bacterium can reproduce by just splitting, the more bacteria you have, the faster you're adding new bacteria every hour. So f prime of 10 would be larger because f of 10 is larger. More bacteria reproducing means more are added every hour. And last one, if the supply of nutrients is limited, would that affect your conclusion? So this is done a lot in population modeling. You guys will definitely see this later in this class, and again, you'll see it in differential equations for sure. So if the supply of nutrients is limited, which one of these is going to be bigger, f prime of 5 or f prime of 10? It turns out we don't know which one's bigger. Because what if it's a very, very small supply of nutrients? By the time there's five bacteria, or sorry, by the time 5 hours into the experiment, maybe all the nutrients are gone. And then the number of bacteria would start to shrink because there's not anything for them to eat. So this would be smaller. If there's a small amount of food, this would be smaller. But if there's a large amount of food, then this could be larger because maybe they've barely made a dent in the food supply here, and maybe here they're just starting to make a dent in the food supply. Well, if they're just starting to make a dent in the food supply, then the population is still increasing at a very fast rate, and if that happens, then f prime of 10 could be larger. So I'll let you read that answer. And understand that there's a lot of critical thinking that goes on here. These problems can be asked lots of different ways. I can ask problems like this on an exam. So make sure you're thinking about anytime you have a word problem where there's some sort of physical quantity being measured, think about what is being represented. Yes, the vast majority of this class is abstract graphs and slopes and things like that. But the reason you learn math, unless you're going to be a theoretical mathematician, the reason you learn math is so you can apply these things in the real world. So think about what the applications mean, and it actually makes the problems easier. And because it's less abstract, you have a way of remembering it, right? All right, last slide. I already showed you guys the animation, right? So we have some book exercises. You can try those. And of course, the homework tutor covers a lot of these problems. Just understand that the homework tutor kind of writes everything more densely. So the homework tutor is not going to separate those limits away from the algebra the way I do. It's fine if you do it that way. Just don't let yourself get mixed up because there's so much notation on the paper. On an exam, you have to show notation. I don't care what method you use. It just has to be something approved. Obviously, anything in the homework tutor is approved. It has to be some approved, method, and you have to be able to back up what you're doing with work that you're showing. And last thing, of course, at the bottom, if you have questions about this stuff, you can search any of those websites for any of the keywords in the presentation. You'll find some really nice stuff. So that's it for this video. If you got any questions, shoot me an email or post something in the discussion forum. So that's it for today. Bye-bye now.